For questions, there will be a HackMD webpage where you can freely write. So I will start sharing my screen, and then I can show you quickly how it works. So you should now all see the presentation. In the chat, there will be a link to the HackMD, and from there, it looks something like this. You can log in and actually edit the document, or you can always, without logging in, make a comment, and then we can also see your questions. So yeah, we also really looking forward to make this a interactive event. So please ask as many questions as you want. And yeah, we have the document to make sure that it's not like double questions and to keep the overview. That said, I think we can get started with the presentation itself. I still see people dropping in, so let's start a bit general. Basically, this is already all introduced. We will have a quick program where I tell a little bit about Delft Open Hardware, a small introduction to get yourself started, and then we will have Sanli taking the floor and giving his talk. And yeah, just to get everybody started and hopefully thinking a bit, I wonder if everybody or if anybody basically knows what this patent is about. If you do know it, please do share it in the HackMD already. Personally, to me, it's just a number. I had no idea which one, what patent this was. But maybe if I tell you that this patent is made by Niels Bolman, I already gave away a slight other hint. But to me, this still, in the beginning, didn't ring any bell. And Leslie, I can tell that he was working at Volvo when they filed for the patent. So maybe you can already feel something up and coming. But basically, the patent itself had to do with car safety. And what they did is Niels invented the 3-point seat belt. And he was an engineer at Volvo. He invented this, and Volvo then decided to share this patent openly with all other car manufacturers. And that was really interesting to see, because then it really got adopted very quickly, and it's estimated that it saved, well, possibly millions of lives. So this is something that really helps to drive science forward and engineering forward, and to see this great adoption widely once you share something openly online and make it possible for others to use it. And that's basically also what Delft Open Hardware is about. So we try to bring together students, researchers, but also anybody else who is interested in open hardware to basically master this skill of making a project open hardware, doing this documentation. And in that way, we hope to be able to share projects and to contribute to a world that everybody can basically benefit from. And yeah, we've been doing this for a bit now, and basically we do this by organizing workshops, having people learn about hardware, about documentation, about organizing projects. And we also make our own projects. So for example, we have sort of an air quality sensor, which measures the quality of the air. We have some students working on like a circular solar panel, some centrifuge. My personal graduation project was a plastic scanner to identify different types of plastics, which also has some documentation open source already, but will be elaborated more in the coming year. So in that sense, we really try to broaden the sense of open hardware. So yeah, that's basically in very short the things that we do. But there's also a guest speaker today. Who is Sanli? Well, Sanli is an associate professor in experimental physics at the Utrecht University. But not only that, he's also a big advocate of open science. He even makes a whole podcast around it called The Road to Open Science. And he also co-founded the Climate Help Desk to make this gap smaller between science and actual action, and just help people answer questions around global warming and the whole climate. So with that said, I would basically give the floor to you, Sanli. I will stop sharing my screen, and then from there on, feel free to further elaborate on who you are and share your work with us.
Yeah, thank you very much, Jerry. It is a real pleasure to be talking to your community, which is, I think, still an example. The open hardware community is an example for other universities. I hope more people follow that. The Road to Open Science also has an episode on open hardware, and you'll be surprised at who is talking in that episode. That's Santosh and Jose. But it's a very nice episode, so I strongly recommend. It's also my moment of thinking about what we are actually advocating for, why we do this. I want to start sharing my screen now, and I have to also have an explanation that some of you might have been at the Open Science Symposium a few weeks ago at the science faculty, and might have seen part of this talk in some form. I haven't touched that much, so sorry for repetition there. Do you see that in the correct format now? Yeah, okay, I see your head moving, and I want to see that as well. Okay, I have asked Jerry to please keep your questions in the chat. I would give 2 moments because my talk has almost 2 parts, which one part is a bit combination of philosophy of science and my view on technology, and the other part is really hardcore science, I think, or technical part. And I would like to give a break in between, but let me just finish the story of each part. Then we can have discussions. The talk is about Fair Battery Project, and I learned a few years ago from George Whiteside, who's a very famous chemist at Harvard, but also very, very successful investor and technologist. I think he is one of the shareholders of the DNA sequencing company, and a lot of other inventions. And he had a talk in the academy in the Netherlands to receive his medal. And he had a very nice part of it. I show it in my classes that said, many people, students especially, when you ask them, what do you do for research? They can have a perfect answer. They can talk 5-10 minutes non-stop about it. But when you ask them, why do you do this research? They usually actually hesitate. And not everybody thinks about the why of doing research. And answers range from, because this gives me a degree, or my supervisor told me, all the way to some very futuristic vision of life, but not as specifically to that research. And here I would like actually to first start of why we are doing this open source battery, and then go back to what are we going to do and how are we going to do that. That's why you have to bear with me for a few minutes. This has been made possible by a very small grant, now followed by a bigger one from the Center for Unusual Collaboration, and they actually granted us this money because we were doing something unusual, which at the end of this talk, I asked myself why this is unusual at all. That makes a lot of common sense in my view, and I will ask you if you think the same. Okay, starting from self-reflection, you probably, some of you might know this person, Martin Shkreli. He also by some people called the pharma boy. He was in the news a while ago. He was in the banking sector, and after a while bought this company who makes this drug for use for AIDS. And then because he had, talking of patents, he had the sort of the rights to decide on the price of this drug. He said, yeah, I'm the monopoly, increased it by 50 times the price of that drug. So many people could not afford it. It made a lot of people very angry. He did one other thing. He also bought one copy of an album. I don't know. I'm not a fan of this band, Wu-Tang Clan, but the fans were very upset because when he bought the album, he said nobody's allowed to listen to it anymore. And it raised a lot of objection. And at some point for some reason, not connected to his acts, these are completely legal actions, he was taken to court. But in the United States, they have to have an impartial jury. And this person was in the court, but they could not find an impartial jury. And there's a Guardian article about the story of finding a jury, because there were not enough people who didn't hate him enough, hate him at all, to be on the jury. He was so hated that the court could not form a jury in the United States. It took a long time because a lot of people say, yes, I know him and I hate him. So he could not be impartial. And yeah, of course, it's an extreme, but this is actually, if you look at the essence of the action, such actions is quite common, sometimes very rational. And, sometimes even maybe, my elderly neighbor also can defend it. Of course, if you own something, you can set the price of it. Very natural for many people in the West, also for many people in the South. This other device is a device which I invented or participated in invention. It's now a spin-off from our group. We call it NanoCT. I'm very proud of it, and potentially, in theory, it can also eventually help in early diagnosis of certain sicknesses because it's a sensitive microscope. And I also have a patent on it. I have another one. And sometimes I ask myself, okay, what's different between what makes me and Martin Shkreli different? Of course, he is the investor and the scientist, but for every patent at the very early phases, there have been a scientist with all the best intentions who patented it. And sometimes in the current system of working of university, patents might be actually the only way to make one technology accessible to end users. So there are discussions on the ethics of patents. Patent by itself is a document that is very harmless. It's actually a very good document because it forces the inventor to explain exactly how that person has done it. But all the legal aspects that are connected to it that make all the other absurd stories possible. And I want to answer this question to myself and maybe all together. And a person showed me this graph from the Dante's Inferno and says, there are these different levels of hell that people of different sins reside on. And I ask sometimes myself at what level of hell I'm going to meet Martin Shkreli. And I should be very truthful to myself because actually hypocrisy is one of the deepest levels. If you lie to yourself, you really go very deep in that hell. So we should be honest on that. There are a couple of general myths, especially at the universities, which try to engage and rightfully bring science more to the public, which I would like to try, at least in some sense, bust. The first one is that if you have a patent, then application follows, and if you have an application, economic value follows. So patents and economic values for many people are seen equal. Impact, they call it. The other one is that, at least in the Netherlands, it's getting even more popular, is that PPP, which stands for Public-Private Partnership, is essential for scaling up. And this is not my claim. I think Ben Feringa, the Nobel Prize winner, the Dutch winner for Nobel Prize of Chemistry, was once on TV and people asking him, oh, why do you collaborate? You're so passionate about sort of fighting climate change and reducing the impact. Why do you collaborate with the oil industry? And he said, well, as a scientist, I cannot sort of make my products accessible. I need the companies to make my products, which is a paint or something like that, to be accessible to the masses. I need them. So a lot of prominent people believe that you need the private sector to scale up. And in this dynamics of interaction with the private sector also comes the issue of secrecy. This is different from patent. Patent is the opposite of secrecy, but you have trade secrets. And they say that, oh, if you have secrecy, you have to keep this secret because you will be competitive. And when you engage with the private parties, many times they also ask you to sign NDAs on things which are totally not related to the exact collaboration you're going for, because you never know. In 6 months, you might come up with some ideas that has some value for them. And the patent law is so old-fashioned and so unworkable in this sense that you have to have the whole history of that person under non-disclosure to be able to make certain claims. So secrecy is taken very seriously as soon as you engage in public-private partnership, including with public grants, like from NWO. Let me start with an example why I think this, in some cases at least, is a faulty model. And the example I show it quite often. Maybe you know that person. He's one of the founders of the MakerBot, and he was on the cover of the Wired magazine because at some point he claimed that, yeah, as many microwave ovens that we have in the kitchens, we will have 3D printers soon, and we will send people the recipes of having their gadgets and they will print it. Of course, it's a very nice dream, but for a while in the early part of the 2000 to 2005, it was very popular, became quite fashionable to work on 3D printers by technologists. And well, this company grew, the MakerBot grew, and here I have shown the graph that you are seeing is the stock price or the total value of the company MakerBot. As you see, from 2002 starts, it slowly grows, and around 2010 it sort of hikes up, and at some point it bangs. And it's not very interactive now, but you can imagine to yourself what happened at this bang. Say, oh, this is not the 2008 sort of crash. This is after that. The reason that this crash of the price of this company happened is that somewhere before that, another company, the Stratasys, actually bought MakerBot. And at this point in time, they decided to make the design of this 3D printer, which until that moment was completely open, closed. And then the community were very unhappy, and they just, it backfired. And yeah, they bought the MakerBot for 400 million, and then just a few months later, they had basically 1/10 of that value. And other people talk about even, wrote obituaries for MakerBot. For them, MakerBot was finished. It doesn't mean that actually 3D printer had a bust. 3D printing actually went up. You can see here the continuation of the trend of 3D printing users. The market still grows. This is an old graph I have, but there are, I don't know, 500,000 parts that you can find on 3D hubs, and there are many, many printers still being sold, and many of them are based on open source technologies, and they are working very fine. I have a 200 euro 3D printer. It works very, very nicely. And I'll give you one more example, building on the 3D printing. This is more relevant to the current time. The reason that we are not visiting each other is that the pandemic is ongoing. So this is a technology built on top of the 3D printer. The Opentrons made a 3D printer, turned it into a pipetting machine, an automatic pipetting machine. And I knew these people like from 2017, 2018. They were also part of the Mozilla program that I was part of, and they were 10 people. They were trying to expand their business in the laboratories, build everything based on open source. Of course, the designs of the 3D printing was open source, but then the pandemic happened, and they turned this into a PCR machine in a very short time. And then the peak, if you remember, the very beginning, New York was hit really, really hard. They actually covered all the PCR testing of New York within a month or so. So they reduced the testing result time from 14 days, which is incredible, to 24 hours, and reduced the test cost from $2,000 in the United States, these things happen, to 28. And if you remember this time, it was about, I don't know, March, April, a bit later. This was the time that in the Netherlands, we had this discussion that we could, the health agencies, the GGD, could not do tests, and the doctors were not sending patients to get a test because we did not have enough test capacity, because we were so much dependent on this Swiss company. And it was not that we did not have the machines, we did not have the buffer. And if there are chemists here, buffer is salt and water connected. Of course, you need to know that composition for that machine to be calibrated, for the test results to be reliable. But even I remember the CEO or one of the top managers of that pharmaceutical company was brought to the Dutch TV. He said, "Oh, why don't you give the result of this buffer?" And only after a lot of pressure, they gave the recipe of this buffer. So, we could make water and salt and then have the capacity. But many people were actually getting sick, getting unnoticed. The pandemic was unnoticed because we were dependent on this closed source technology. And this company made it. And if you check it now, very recently, this company has been valued at 1.1 billion, and the third round of sort of fundraising got 200 million to expand. So open source can make economic sense. With these two stories, I'm trying to convince, at least in some cases, in some maybe limited cases, that patents is not economic value. Only plus litigation brings the economic value. So you need lawyers to bring to turn your patents into hard cash, money. Sometimes, or many times, actually, public and private partnerships slow down scaling up, not the opposite. Think of that example, which within a month they could scale up and have PCRs for the whole population of New York. And secrecy obscures competitiveness. It's not equal to competitiveness. I didn't give an example because I don't think it's really necessary. Probably you have read this book or maybe seen the movie, and you all know that how secrecy can actually embarrass even very smart and very rich people by quite a lot. So I'm not going through that. And so that's my claim, that at least at this moment, coming back to the issue of the climate or the energy transition, the open innovation is the way to go for the transition technologies. And these are my reasons. The first is that there is urgency. So this has happened very quickly. Just moral reason that this has to happen, similar to vaccines. It's morally necessary to do it fast. For many people, even now, I think even in the Netherlands, climate change is even bigger than the pandemic in their list of mid-term and long-term worries. In this case, demand is exceeding supply. A lot of people actually require these transition technologies. We don't have the technicians, we don't have the training, we do not have the supply for making it happen. Otherwise, this should have happened yesterday. So you have a market. It's not that you have to invest 20 years and create a market. The market is there. You just have to bring the products. And you can already see that, in the gas prices, for example, demand is a lot for a reliable energy source. At the moment, there is no unique winning solution. I'll come back to it. We don't know what is the sort of the winning technology. So we still need to develop a lot. Everybody needs to develop. Even the Teslas and the BMWs have to develop their technologies. The solutions that they suggest, we know, are immature. The price is not mature, and the solution itself has still problems. You can understand that because they are improving it every 6 months, so clearly not mature. And a lot of R&D is actually public money. A lot of people talk about the 500 million that Tesla got, and where is the back for? But even in the Netherlands, a lot of investment in the R&D on the energy transition is still just based on public money, and very similar to all the research that has been put in developing the vaccine, which was paid by the public purse. the discussion you can have here is that how should we pay, but then don't get the rewards for it, not even the access that we demand. So this is the first part I have. It's a very general argument about having, at least for the critical technologies needed for the energy transition, to have an open innovation model. And if there are questions, then I would like to discuss them now. I will focus on batteries in the rest of my talk.
So far, I haven't seen any specific questions in the chat. Everybody is free to put the questions either in the chat or in the HackMD page. And Santosh just mentioned that you can also unmute and speak if you want.
Okay, so if you do not disagree, I can move on and focus on the battery project. I think that's, yeah.
Cool.
Okay, so, well, here is one of the challenges. I call this the big challenge. That's the fact that, yeah, we need a lot of energy. The energy consumption is growing. And I also got this slide from Gert-Jan Kramer, and he actually said a very interesting stuff. If you look at this lower part, I mean, each time that there is a new energy source sort of getting very popular, it doesn't mean that the other energy sources are sort of going away. And from the 1800 until now, just biomass, burning wood, is still at the same level. And now for the coal, oil, and gas, I mean, all these things should go down within 10 years to zero. And the other ones should grow. This is a very big challenge. And I don't know if anybody knows the magnitude of this problem completely. Well, one of the solutions that they are suggesting is actually to combine electrification is one of the solutions for this huge demand. And luckily, as predicted, we have the prices for solar is going down. It is actually basically the cheapest, solar and wind, the source of it. But because they are intermittent, they are not always available when you need them. They need energy storage, and batteries, the energy storage is actually not getting cheaper, if not the opposite. It's actually getting more expensive. Many of the technologies which are not economic now, they are waiting for the price of the lithium to increase so that those technologies like sodium batteries become economic. That is a big problem, and we do need a lot of storage. So then we said, what is our little challenge in comparison with the energy transition is the question is that can we build an open source battery? And somehow, unlike many other sort of technologies which from science have maybe microscopes, that's my field, have open source versions, maybe rudimentary, basic, but they do have some versions. I could not find any open source battery until recently. And of course, this must be accessible. So it's not enough that it's open source, but only a few hobbyists can use it or build it. It must be also very cheap. And this is a price estimate that I have for this technology to be obtained. On top of that, we also put it from the outset as one of our motivation that we need to use locally available materials and not sort of have to transport a lot of material. If you have locally available material, sometimes you also have locally available technologies to process them. The maintenance is one of the biggest problems. Electrification is a very big thing for development nowadays, but maintenance goes away. And my collaborator on this project, Martin Force, he's working in Africa on electrification. He says, many of the projects of making off-grid electricity fail to give any added value after 1 year or two. And that's because the battery stops to work and they cannot replace it. They do not have local expertise to maintain it. And we would also not to create a new problem. So we want a recyclable solution. And that's how we started with the FAIR battery. And the FAIR stands exactly for the reason that the open science FAIR thing is. It must be findable, so people should easily be able to access it. They should be able to adopt it to their local conditions or the technologies they have and reproduce it. So this is the challenge of the FAIR battery. Can we create such an open source electrochemical battery? That's where we are focusing now. With deliberately using low cost and locally available materials, so that we actually do not pursue the materials which can be very, very attractive for science, but not necessarily for this purpose. Like, I don't know, the goal of mobility needs totally different criteria than the goal of local energy storage. And we also want to set up education communities so that at the same time that we are doing the development, also there would be people who can maintain this the thing that comes. This is about a year. It's still, very small activity in our group, but this is growing quite fast. Where can we go in this sort of domain of energy storage? From this article, I have found all the technologies which are used for storage. It's also not only batteries. So the lithium ion, probably there is also sodium sulfide. Lead acid is the most sort of common ones. This is the battery technology used in cars. And the technologies are sorted as a matter of efficiency on one side and the lifetime, or how many cycles actually you can do it. And if you want something to be useful, you would like to cycle it maybe at least 10,000 times. Let's say that's 20 years if you cycle it once a day. And so the problem of lead acid, even though it's widely accessible and a lot of people can repair it, is that, first of all, it's not really environmentally friendly. It has a small capacity. It only works at a very high charging level efficiently, and you need to actually maintain it quite often. So lead acid was not our solution of choice. There are other solutions which are very much used nowadays, like pump hydrodynamic storage. This is really pump water up to a dam and then use it again to generate electricity. This is actually the most common, or in terms of the capacity, the largest way of storing electricity at the moment. This is, I don't know if you see my mouse, but this is this gray bot. There are also supercapacitors. They are quite expensive, quite efficient, but they do not have the massive capacity that we need. Lithium ion is at the moment the winning, even for long duration storage. People are using it. I heard 2 weeks ago there was a megawatt storage facility installed in the Netherlands. It was based on lithium ion technology. We are focusing on this central one, this redox flow battery, RFB, and I will explain what this RFB stands for. Redox flow battery is, let's say, a variation of the electrochemical cell, which is used, for example, for what is it called? Water splitting to create hydrogen. If you apply electricity, you can actually generate hydrogen. This is one reason to use it. It can be also used for fuel cells when you put hydrogen and you try to get electricity back. So it's the same electrochemical cell. Generally, it's made of 2 parts. You have 2 different reactions going on, and you have the products of it. That you should have ion conductivity during this cell. So you need a special membrane, which is an electric insulator, but an ionic conductor. And the way it works is that you create this potential by the ions, by the chemical reaction, and the electrons go through your circuit because they have different potential, but the ions don't and stay here. And then to close the circuit, ions actually go back and then fill in the charge neutrality condition. And you can create, depends on the electrochemical conditions, which I will explain. You can create maybe with one stack, only 1 volt, and you can stack them on top of each other. You can create many volts. This is almost similar for all the batteries. The speciality of the redox flow battery is that you have this cell, which, the reduction and the oxidation processes happen, but then you have a lot of storage by pumping your material outside your cell. To show from this picture, you have a very small sort of reaction area where the magic happens, and you have this sort of potential created, but you need to feed it with the new material. And this new material can come from a storage place. And unlike the lithium battery, where the storage and the reaction happens in the same battery space, in the same area, here you can actually bring your stored energy outside your cell, and you can increase it as much as you want. So you can actually tune the capacity of your battery separately from the power provided by your battery. And this is quite sort of a flexible way of building a battery, and that's why this is sort of suggested for grid energy storage. The downside is that your energy is most of the time in a liquid, and the ion density in a liquid is usually less than the ion density in the solid, and that's why you need a larger volume of your storage material. And generally, these things are not so lightweight, so that you can, for example, use it for mobility, although for some sort of heavyweight mobility, these are also considered. But there will be no, I don't think there will be a personal car with a redox flow battery. It is quite old technology. This picture is a courtesy I got from slides of also Michel Sakes, who is really a battery guru at Vetsus in Leeuwarden. And yeah, this is a picture from 1836. This is one of the first examples of materials used for redox flow battery, that you have copper and zinc. And you need these two different materials that they have different electrochemical potentials, and that creates actually in your cell the different potential level of the two ends that you actually need to use for creating the flow of electrons. And he made it back then with ceramic separators. These are these things in between the ceramic separators, and then you have inside a zinc metal plate, and the outside the copper reservoir, and then the electrolyte is some form of acid, sulfuric acid, that goes actually into this ceramic separator. But it's more than that. So most of the people who talk about batteries talk about, at least this type of batteries in the science community, talk about the chemistry going on, and it's still, that's the area that needs the most development. But that battery is more than just the chemistry of it. You need to have a very effective flow of this energy material into your system, the distribution. So there is a lot of process engineering going on. You need to control the electricity flow, the battery management system, especially when charging. Otherwise, you easily can create water, or you create, I don't know, hydrogen, and your battery can explode. The issue of durability is a matter when you are talking about, I don't know, 20 years and chemistry at the same time. A lot of things should be taken into account. Things should not precipitate. They should not corrode. There must be no leak. So it is a big issue, durability, and also the materials. We are talking about really huge amount of materials. So some of the materials, they must be available. For the case of lithium, for example, cobalt is one of the elements which are used in the electrodes. And the lithium itself, it's not a big problem, but for very efficient batteries, that cobalt is one of the elements which a lot of people haven't found a better replacement for. There are solutions nowadays, but still a lot of batteries use cobalt. And as we know, there is very limited supply of cobalt, and usually it doesn't come from very ethical sources. There are many examples, because it is now chemistry. You have the whole periodic table, at least a part of it, that you can use. These are some of the examples of people have been using these combinations in redox flow batteries. You can have sulfide, bromide. The first, all of them are actually water-based, and I even didn't list the non-aqueous based on other solvents like acetonitrile or organic solvents. The one which is on the second one, the vanadium, is one of them that is quite commercially viable, because it has a lot of good properties. Today we will focus mostly on the iron redox flow batteries, but there are many types. I think in Delft there's also a company who works with zinc bromine. In Eindhoven there is also another company. They try other ones, and as you will see, to get it working in the lab is one thing. To get it work as a battery is totally different project. I want to focus on the iron redox flow battery, because that's what we hope to make into the open source battery we want to make. When you want to understand this electrochemical cell, as I said, there are two reactions going on at the different sides, and these reactions go at different electrochemical potentials. For example, for the case of vanadium, in one side of it, you have vanadium 2 plus. This is just the ions, which is important. Of course, it's a complex in a bigger molecular structure. Will give you the electron that you need. Will release the electron at this potential. And on the other side, there is another level of vanadium that actually gets the electron and then gives you another form of vanadium oxide, and some water. And it happens at a different potential. And if you want to find out what is the potential of the cell, you have to subtract these two from each other. So the potential of the whole cell will be 1.25 volts for one single cell. Similar thing happened for iron. So all iron is also that you have two different reactions of iron happening on the two different electrodes that you have. In one side, your iron actually will be reduced, so it gives out an electron. On the other side, will be oxidized. And these are reactions which in chemistry you can help to assist to become the favorable reaction. You have to keep in mind that also there is water, and this reaction should have higher priority than the reaction that happens with water, when you which is creation of hydrogen and oxygen. And this is one of the main problems with iron. I'll come back to it in a slide. The reason we are considering iron, even though the vanadium shows to be more mature, is that iron is much cheaper than vanadium, 60 times cheaper, and it's also much more abundant. Everywhere you can find iron. Vanadium, it has fluctuating cost because it's also not so abundant, but also is highly demanded for making sharp tools. You probably have seen, if you have used a drill, there are some of them shown that there is vanadium inside. It makes the steel very, very hard. There are, of course, challenges for the all-iron battery. One is that it happens as a certain potential window that is also favorable for hydrogen splitting, water splitting. And this will, if you have a lot of hydrogen, first of all, you lose efficiency because your energy is not stored in the iron, but it's stored in the hydrogen, which can escape your system. You have actually mass loss. You always have to add water. And it can also be dangerous. It can catch fire. So one has to play with the chemistry and the geometry to actually make the iron reaction much more favorable than the hydrogen reaction. And this is mostly done by adding additives, changing the pH, for example. Also, if you play with creating hydrogen, you also change the acidity of your system. And if you change the pH of the system, also the reaction again changes. So that's also something to be controlled. And if you go to basic conditions, then your iron actually forms deposits, and then when it deposits inside your cell, you can no more actually recycle it. So it's a lot of control that has to happen for this battery system to work. But people have demonstrated it, so it's possible. One of the theses that Michel Sakes brought to our attention is this all-iron battery. It's an old thesis, now about 7, 8 years old, although this technology have been later actually being used in one of the companies which is now in the United States. And this is all about an all-iron battery, and the technology they used to make it very sort of commercially viable or close to application was to add carbon material into one of the electrodes. So the reaction problem that we have is, I have to be careful now. Yeah, so on the side that the iron is actually sitting on so one side of it you will have a reaction inside the solution, but on the other side your reaction will be by iron actually going from something which is dissolved into iron metal and deposits on your electrode, and this is how it is stored. The same happens in lead acid. You basically deposit lead, and then when you use it, you put the lead go back to the solution. So here you deposit iron on the metal that you have, and you grow it, and then when you want to actually use the energy, you actually etch the iron away from the metal. So the solution they had here is to actually reduce to increase the efficiency and reduce the resistivity of their cell by adding carbon nanotubes into their cell. It doesn't need to be nanotubes, it can also be carbon flakes, but if you add these sort of carbon particles to the electrode, they can actually connect to each other and then make a sort of a chain. This is called percolation. And on this chain, you actually can also bring the electron from your separator where your reaction is happening, or from the inside the solution into your electrode, and then make it useful for the circuit. Otherwise, the electrons will have a hard time to go from the place that the reaction is happening to the electrode, because there is internal resistor which is very high. So with this trick, they can actually reduce the internal resistor of the cell, and that's the one use of these carbon particles. And the other use is that actually the iron, instead of sitting on the current collector, it actually sits on the particle itself. So you actually store the material where the energy is stored on the particles, and then you can recycle it again and again. The downside of it is that it makes your material very viscous. And if you put a lot of these nanoparticles, then you cannot flow efficiently, and that also consumes energy. So there's a sweet spot for that. There are also other things, and at the end, I think the battery which the company is going to sell has many other additives to control the pH, to make sure that, for example, hydrogen evolution is not happening. So there are other tricks that has to be played. I still have 5 minutes, I see, from my presentation, so I think I'm right on time. This is about the chemistry, and there are many other chemistries, but once one focuses on the chemistry, one has to also try to optimize that. And this is actually one of the parts that actually breaks my heart a bit, because we do not have standard cells, and people you have a lot of papers. We have found 60,000 papers on flow batteries. They all do different tricks they play, and they report it. It's sort of available science, but you cannot compare them because they have done it each in their own sort of laboratory cell. So having an open design to begin with can help people to standardize their reporting. This is one of the projects that we want to do with the support of MBO, to just actually bring all these reports into one format, have a sort of a metadata for the batteries. For lithium, actually such a thing exists. For redox flow batteries, I haven't seen that yet. That's one thing. But then we are talking about a cell, and then cell has, I don't know, 1 volts. You cannot run a house on 1 volts. And it can also show that it is actually not, you will have to have huge currents going through this cell. There is a current limit. So this is not really attainable, useful for storage of electricity, which you can use at kilowatt level. So one has to make stacks. And when you make stacks, because these are sort of floating potentials, you add up also potentials. So if you have 80 stacks, you will have, I don't know, 12 volts or 10 volts battery. And then you have manageable currents. You are talking about 50 amps instead of, I don't know, 500 amps, which is huge current, and then it will break your membrane. So people make the stacks. On the lab scale, it looks like this. It's a very small object, sort of, and then you can put a lot of intermediate filters, and you have to seal it all. It's not trivial, but once you do it right, you actually just put all these filters and levels on top of each other with the correct flow management. And this is a commercial, on the right, you see it's a commercial Chinese vanadium flow battery with, I think, 48 cells connected to each other. The liquid is in these tanks, and the liquid is flown, and then, yeah, the battery actually works. I could have purchased it. They offered, I don't know, this for 10,000 euros, but I should have picked it up from Shanghai, and I didn't want to do that. But this is also one of the things we will consider. If we actually don't manage within a year to build our own battery, we will actually focus on having one of these commercial ones and try to reverse engineer or just maintain it ourselves without a company needed. So this is one of the things we can consider. But this, as you said, this becomes one of the other aspects. It's a very interesting, has a solution, but a very interesting engineering problem, how to build this stack. It also makes it an electrical engineering problem, because once you have one cell, you are in charge of how much potential you apply. But when you have a series of cells, you only are in charge of how much potential you apply to the two ends. And you are not really aware of how the potential is distributed within the cell. And we know that we want to keep it within a certain workable window, let's say between 1 and 1.5 volts per cell. But if you have 50 volts across your cell and somehow there is a short circuit in one of your layers, then the next cell will actually create a much higher voltage, and the next cell will also, and then you will have a sort of a chain reaction and then kills the whole battery. So if you see the sort of laboratory scales, they have electrodes to control every one of the cells in between. It makes your electronics very complicated and expensive. So to make a stack that doesn't need to have control on every level of the single cell is also by itself an art, which is not so commonly explained in the literature. So this is an extra challenge, but as you see here, there are solutions. You need now electronic control. You have to control the current you apply. You do not want your battery to burn or cause fire. And this is done by battery management system similar to the cars. You know, you need that. If you know that if you actually apply too much potential, you will just burn the battery. Luckily, on this part, there is an open source solution. It's called the Fox BMS, made by the Fraunhofer Institute. It's also a very funny story here. But they have provided it. Mainly, they developed it for the car industry. That's in Germany. But they have later also converted it to solutions for flow batteries, although it's not optimized for flow batteries. So this is also one thing we took to ourselves. I can tell you a fun story about Fraunhofer, this Fraunhofer Institute in Erlangen. I used to live 2 years. It's not even Erlangen, it's a small village, Tennelohe. But I lived like across the street from this institute. And I already then heard about it in my institute, in the Max Planck Institute, that, yeah, this is a very good Fraunhofer Institute. It has brought the biggest amount of money to the Fraunhofer system in Germany, 200 million. And why was that? Because, well, they had a patent on MP3. So for a very long time, for every MP3 that people played, or I don't know, Shazam, or it didn't exist Shazam, but I don't know, all the computer systems that play MP3, they had to pay, I don't know, a few cents to them to get the license and become very rich. But even that institute, which is a semi-public institute, has decided that, okay, once I got my research money from the car industry, I can say, make what part of the product I have that I can open source. And I found that a very, very nice move. But for our project, this has to be actually adapted to the redox flow battery and maybe even a bit simplified, because this is very, very high-end battery management system. One of the things I did last year was actually to test it with a class of students. These are physicists, not chemists, but physicists. We had to test if they can learn about experiment design. And we said, okay, can you split the battery into pieces and then build it? And actually within like 2-3 weeks, the course is longer, but they had only 2-3 weeks to make things. And they sort of managed. They could manage to make one of these cells, but also to build a battery control system from, it's not open source hardware, but from an available A2D card, not very expensive one. And they could run it, they could show that it works. They also chose the name Flower Power for themselves. I think most of the people, including myself, are not of the age to remember the Flower Power years. If somebody does, raise your hand. But it's possible. It's possible to split into smaller pieces and then work on it collaboratively. And that's our plan. So in 2022, and maybe a little bit of 2023, what our plan is to, first of all, to build this database, online database, or let's say Wikipedia of all the papers on flow batteries and all the materials that have been used, so everybody can use, and hopefully the new reports come also with that format. We hope that we can design an open source stack. This is it's quite a challenge. I'm happy that very recently a group at Eindhoven, a group of students said we want to build a stack. So, but maybe we actually make it a competition in the next year. So if you see yourself up to the challenge, or you know people who are, send them our way. Maybe we make a competition for an open stack. We need to adapt the battery management system to our flow batteries, either the commercial one we buy or the stack that we build. It must be interoperable. We would like to actually install one of these all-iron batteries in sub-Saharan Africa, probably in Sierra Leone, and in a clinic, to see if actually they can maintain it, and what do they miss to maintain it, what type of education they miss, what type of technology they miss, what type of materials they miss to maintain that system. They now have lead acid, and they do maintain it locally, but we want to see if they can do it also with flow battery. And we also want to identify the supply chain, and whatever in the supply chain that they cannot buy locally, we are going to find out why they cannot and make a report of that. And also monitor the maintenance. And as I said, I'm not going to do a lot of these things, but I have good collaborators which are actually specialized in studying development economy. And they are going to do that. They have a lot of experience with working with these local communities. To summarize both part of my talk, I think open hardware is a sort of should be a pillar of open science program. It is the case in Delft, but must be also in the whole Netherlands. Yeah, I think open science and education, they are a match, really very good match. You can use open science for education and the opposite. And the flow battery that we had was very useful for our education. And I also make the claim that at least in the case of energy transition, it must be open source. Otherwise, it will not be up to the task. And yeah, if you have money, I would say invest wisely and invest in open. And at the end, yeah, a fair battery can be a fair battery. That's my claim, but other people may disagree. These are the people which at the moment we collaborate with. Nicolas actually is from Delft. He helped a lot in the last year to make this sort of software for controlling the batteries or monitoring the batteries possible, and supported us with the development. There was a student project who started to make the first cell, but then the whole group of the in my class, they built 2 cells based on that student project. These are the group leaders. They are experts on different aspects of the battery technology, but I would especially emphasize Stephanie and Martin. They are actually just in this project because they want to study how this project or a battery can actually have an influence on the local economy in an off-grid and rural area. And luckily we have now money. That's good. We have quite a bit of money to spend for the next year. So there are more than one position, couple of positions available now, both from resources of MVO and the Center for Unusual Collaboration, both to build stuff, to maintain this education program that we have to do, and also to dig into the data of these articles. So all sorts of activities are supported. And that's it. I think I can end the show.
Well, thank you very much, Sanli. That was a super nice presentation. And I think in the meantime, some people already put some questions on the HackMD. So I think what I can do is see if I can share my screen, and then hopefully we can go through some of these questions. So let me see, share, you should now be able to see my screen, and this should be bigger, and we can do this one. Okay, cool. Oh, let me see if I can zoom in a bit. Ooh. Okay. Yeah, so the first question is very much related to Delft Open Hardware, and I think Santosh wrote down a super nice answer already. But some of them specifically about the presentation. This ion selective membrane sounds very special. In the presentation, you also mentioned that it should be recyclable and hopefully from available materials in different places around the world. Is this thing very special, or is it just a piece of corrugated metal, or I don't know?
No, that is true. So the ion selective membranes are quite specialized, and the good ones, which are used with the high efficiency batteries, are all from companies like Nafion. Even they don't have chemical names; they have these company names. Nafion is one of the most famous ones, which I don't remember which company it is, but you can only buy it from that company. These are very special polymers, and they also do magic. I mean, as a scientist, they are the most interesting part for me because they somehow guide the ions but don't let the electrons go in. So it's quite interesting.
Yeah.
But luckily for the flow batteries, you don't need always. It helps for some of the chemistries to have the ion selective membrane, but not always. Generally, you would like to keep, if you have two different type of materials, you would like to keep these into different boxes. Otherwise, over time, they will just combine and then you will have equilibrium. So if you, certain types, you have a problem. In all vanadium and all iron, you can actually circumvent that, because even if the iron sort of escapes, goes to the other side, it reduces your efficiency, but then later you can charge it in the next round. It's not true for the other ones like chloride or natrium. So sometimes you need this specificity. The other part you can do, so you can leave with just the separator. This is called the separator, which is an insulator which sends through ions. And in the example I showed you, the ceramic is just a separator. It sends through the ions, but it's a very good insulator for electrons. And there are many more. I mean, there are good separators which are much cheaper, maybe 5 times cheaper than the Nafion, for example, the membranes. But eventually, with one of the reports, you can see that maybe up to 30–40% of the price of the battery can be the membranes. Especially if you make a stack, you also need a lot of them, and the area matters.
Yeah.
So that is one area. Also on research, it's not on. So you can also change a lot of properties of the existing membranes and increase their efficiency by treating them. This is also a very active area of just research. How can you treat, for example, a plastic membrane with carbon graphene, for example, to make it more selective for iron. But for us, we are going to probably just use separator, which is what I said, an insulator which lets ion diffuse through. It's like, I don't know, ceramic.
Yeah, and I think that totally makes sense if you want to make sure that people will actually build it and that it's possible to replicate it. So
yeah.
Okay, that's good to hear. And I think that also, well, the question was already answered why you chose for iron, but basically, so not only because it's cheaper than vanadium and more available, but also because you can use this separator, for example.
Yeah.
Do you know if the battery you showed in the presentation from 1836 is still working?
I think actually Michel mentioned that even that picture is a replica.
Okay.
It's not the original one, so I don't know.
Yeah. Because in the end, there's still a limited amount of cycles. It's just the way how you refurbish it.
10,000 cycles with recent batteries, and 10,000 is a lot, right? If you divide it by 365, it is still many years, and that's already very good. I think by all standards, it will be called infinite. The question of the lake storage volume also found extremely interesting. Actually, one of the students in the class calculated. That's the funny part. So when this is the difference between the mass energy, we can philosophize on this, but the energy that you can store in moving a mass in comparison with dissolving an ion. And if you want to compare, we did a comparison that if you want to have the same energy, like, if you have around 10 molar solution, for every kilogram of that you store in your tank, you have to displace it, I don't know, 70 kilometers above the level of Earth, so that you have the same amount of energy stored in this, in sort of gravitation energy, if you call it. What is a good, in just mass displacement. So if you say lake, of course, the lake or dams are very good because they have huge areas, but you also have to have them very high. And it soon becomes a facility. It is not something that you can put in the back of a car or a truck and then take it to, I don't know, rural area. Plus, one of the problems with hydro storage, and this is already a big problem, is that many places that need this energy, water is a scarce resource. In my country, right, there is a lot of mountains, but there are also a lot of Iran, my birthplace. There is also a lot of desert. And over the time, there is conflict, because if you put a dam on the river, places that had access to water, they no more have access to water. So actually make neighbors enemies because, you did a storage. And it also creates huge damage on the environment if you do not do that controllably. as I said, storage already is done by putting water in high reservoir like a dam or a lake, but it's not a universal solution.
Okay, cool. Interesting. Um, so I already also see some other questions more on the side of open source hardware related. So here was a question: you gave examples of open source hardware doing economically great in terms of value on market. Should we also look into other types of economic success? Linked to this, isn't the open source hardware community anti-capitalist? To a certain degree, at least making lots of money is not an objective. Is this something you have a immediate...
I mean, this has come to the example. I don't think all the open hardware community is anti-capitalist. I mean, some of them are pretty much, faithful in having investment, and I don't think everybody is like that. Of course, what do you want to money, right? There must be things that you can buy with that money. And when things are not developed, you cannot buy them. So you have to spend on development. And sometimes if you need this, next year and it's faster in development, if you make it open or more reliable, maybe that's the way to go. I had also one other example. NASA recently sent this small helicopter to Mars, and the software that is used and also the hardware used for that helicopter is open source, because that's much more reliable than what sort of other companies could do. And it's the same software that you can also use for the drones. The same with Linux. I think it's similar. There are two separate discussions. If you want things fast and reliable, I think openness is the way to go. What can you do later? You can also just make it open, but like Microsoft, I don't know, monopolize the system. This is another way of getting money from open.
Yeah, and I also think that in the end there is a lot of gradients between something fully shared open source online and something fully closed, and a lot of business models in between. Yeah. I think Santosh also wants to say something about this.
I just wanted to jump in with that. So Sanli mentioned the podcast that he did with us, Jose, myself, and him. I think that one actually has a little bit of conversation about this specific question about economics and what works and not. The other thing is that there's a big question about different economic models or different ways of doing this. One of the young researchers, entrepreneurs, were partnering with Simon Brinkma. He's also there in the call. So Simon, feel free to jump in. We are partnering to see how an open source business model would work, right? So I think sometimes we think of these things being in conflict, but they don't always have to be. And we can find a way in which that we can avoid the exploitative elements of some economic models, while at the same time using the systems that are available to scale up or reach a wider audience. Simon, do you want to say something?
No, not necessarily. I think it's a very interesting question, and yeah, I mean, I think we've seen examples of it happening, but I also think we see, yeah, and this is something we were talking about yesterday. In the world of business, there is a sort of aversion towards open source, and in the world of open source, there's an aversion towards business. So I think practically it's possible, but in culturally, there is often a lot of difficulties.
Thank you, Simon. Jerry, I think there's one more question left. What do you think? I'm not sure what that question was supposed to be.
Yeah, actually, I was writing that question.
Go ahead.
So what I wanted to write was, at the end you were talking about open science, and I wanted to ask, like, what do you find helpful if you work on an open science project? or maybe even specifically an open hardware project? Do you have tips for documentation or for talking to people, explaining your project? Is there something that you think is quite handy in the development of such a open project?
Oh, that's a very big question. There are many things. Maybe I once listed seven things for one of my talks about. Try to remember this. I mean, one of the very basic elementary things about the open source project is that really have an idea of why do you want to make open source. Sharing and expecting other people to work, it's not gonna work. The people are not waiting, clicking, oh, what's the newest open source project I can contribute to. So from the very beginning, you have to find out what is the value of creating this, and that sometimes you have to even make stronger choices than when you are, on a payroll of a company that says, just create some innovation in the next 2 years or 6 months. Here, you have to really think very hard to choose which direction you want to work. So you would like to have a very, very noble cause. And yes, so I would say economic success could be one of them, but you cannot make everybody rich, right? We had recently in this Robinhood app that somebody found that if they trade, I don't know, the game stocks, they can be rich, but not everybody could become rich. So people engage in such a massive sort of trading for ideological reasons. And sometimes fate is much more sort of stronger motivation than economy. It doesn't need to be anti-capitalist fate. It can be also, libertarian fate, or many people who started with open science, and are still continuing with open science, also in software, they had very right-wing libertarian ideas. Peter Thiel is one of the examples. So you have to think about it. Which community are going to do it? What values you would like to have? And how are you going to actually manage your interactions with the community? And if you think that, this community thinking is not something I want to engage with, probably you should not be starting a new project, but just join and then let the community part be done by somebody else. But this is really, really essential. You need to have a very big goal that a lot of people can identify with. That's one of them. And the other one is that also think about it as a very long cycle. So always find out how you're going to grow, or when the community shrinks, regrow your community. So documentation in the sense of your technology to be documented is very important, but also your process. What is the history of your activity? That's very important. A lot of people who even are willing, they feel a barrier after a few years to join your activity because they don't know history as much as you know. And you would like to make it sort of transferable. We are not so successful yet on the Fair Battery on this, but in the Klimaathelpdesk, which we are also based on a basic open community principle, we have been very sort of careful on making the Klimaathelpdesk documentation open. So we also recorded all our previous meetings, but also all the structure of the questions, and that makes we have a lot of turnover of volunteers. Volunteers come and go every 3 months, and we still have kept it at around 30. And it was extremely important to keep that sort of lower the barrier for the engagement of the community and then keep them motivated to recommend to others. And people have a lot of other hobbies and occupations to go back to. That's the other part. Again, come back to the community, but on the documentation side of your community.
Cool. That's super nice to get a little insight on how you go about with these projects, and giving the example of the climate help desk and people helping out. And in the end, you will always have people come and go, and it's already super nice that they contribute their time to a project that you help started. So that's great to hear on how you sort of go about with these things. Simon, is there something you would like to add as well?
Yeah, thank you, Jerry. Yeah, I think related to what Santosh was saying and I was saying before, I still wanted to raise a question. And that was also related to the question in the HackMD group about success and other types of success. I personally experienced that dreaming is very important. You need to have a, yeah, I think for humans in general, it's important to have some kind of vision of what an idea can become in the end, to know what you're working towards. So that's what I want to ask you. How do you define success, and what is, if you can think freely, where do you see the Fair Battery going in, let's say, 5 years, 10 years, or 20 years?
Okay, well, yeah, dreaming is of course very important, but also your dreams should be shared. So I don't think my dreams are necessarily the best ones. For the batteries, we of course imagine the prevalence of 3D printers as we have it now, and many people have used it also in sort of less developed places as a tool to jumpstart their research lines or their local businesses. I hope that this would be something along that path. So my hope is that many people who even don't have access to sort of grid electricity will eventually find out this way of having a local small grid setting up and then being able to maintain it. So I hope that as many fridges that we have now, at some point we will have batteries. And you can argue that, oh, the fridge is not open source, but the design of a fridge is so old that it's almost open source, right? You can start designing a refrigerator from a lot of technologies that we have. And I think, and I don't think I'm the only one who thinks that in maybe 20 years or 30 years, as many as gasoline or diesel tanks that we have all over the world, we will have batteries. There is no way around it. It is, I think, a count of 1 billion. And if like, I don't 1% of these 1 billion batteries is open source battery, I would be happy. It doesn't need to be overflow open source battery, but people should have open source batteries access to. Same with the vaccine, right? The vaccine that we have, the patent ones, is not supporting the whole world. That's why there are people, I don't know, Texas, one example, who say, eventually we will need open source vaccines.
Thank you.
You're welcome.
Yeah, and I would also like to ask everybody if they have questions or if they want to speak up, then please just unmute yourself. I would say from now on, it's a very informal discussion on either batteries, on open hardware, on open science related topics. Before everybody leaves, I still want to already give you like a small thank you, Sanli. So we made a little card, and we will send it over the post. Unfortunately, we cannot hand it over to you directly, but
Netherlands is small.
Yeah,
I still have your little board in the workshop of last year. So
yeah, cool, cool. Yeah, we will also add some stickers in there, and I already see more people turning on their screens, raising their hands. So yeah, the floor is up to you guys.
I see a hand of Narika.
Yeah.
Spelling correct.
Yeah, thank you. I just put a comment, so maybe I wanted to get in. I wanted to thank you for excellent presentation. I enjoyed especially the first part of your presentation, and I actually agree with everything you said. That's why I haven't had any question about it. But I really do like, I know you talked a lot and answered the questions about the economical part of the open hardware and generally open source, I believe software as well. But thank you for mentioning the topic and the importance of open hardware in education. I think it's quite important that we have open technologies so that we can learn our students how things function, how they can repair things. I'm coming from engineering field, that's why I'm thinking about that. And also how they can hack things or maybe prevent themselves from being hacked. So that's maybe more a comment to you, not a question, but here.
Well, thank you.
Keep
If
up
you
with
want the
good work.
slides, you can have them, and please spread the word. If you want also talking to other communities, please spread the word. I fully agree that we need technical. I mean, when I was studying, which is not very long ago, it's still long, like 20 years, we had, you know, general technical instrumentation, even in the physics program, but now we don't have it. And I tell you, I mean, number one wish of my physics students is to learn soldering when they join the course. So we put a soldering course for them. We somehow lost it, and it's a bit like, you know, losing the skill of I don't know, skinning a chicken when we used to do that, or that's very sad that we cannot sort of solder our own boards. And this is coming back, and it's only possible thanks to open hardware nowadays.
I agree. Thank you. I also learn my students how to solder their boards at the university, and I think it's important. Probably they're not going to do that in their career, but they should understand the process and the work so that, I don't know, they can work better and be better engineers or scientists one day. So, thanks.
Hey, Jeroen. I see
Hi,
you.
Sanli. I've got a question for you.
Great.
And that is, could you talk a little bit on what, according to you, are for your project for this battery, the most pressing challenges, but also opportunities? What is it that you would most like to see? What you need? Is that money? Is that knowledge? Is that collaboration? Is that exposure? Is there anything you need that is difficult for you to organize or arrange?
You won't believe me, but people.
Mm-hmm.
People with the right ideas and philosophy, which don't have their hands, full with 10 other projects. Luckily, at this point, we do have money, but the right people, to find the right people, that has been difficult, right? I cannot sort of count on very sort of graduate students because they have other plans, and this is a one-year plan. And also, the other type of students are too young, so they have to be trained. So people, and that's again connected to education.
And that's people with what kind of skills?
All sort of, like from data mining to do, literature survey, automatic literature survey, all the way to designing mechanics, electronics, and these type of things. This is the part. We have positions, we can pay them, but to find the right people has been the most difficult thing so far.
Okay, thanks.
Yeah. And if I find them, then I would spend, I don't know, another few months developing our prototypes to show off, and then I will go for exposure. I mean, now we only have prototypes, and some people say, oh, you do not have a battery, and I agree with them. I do not have a battery, but I have the vision. And other people say, okay, call me back when you have something I can install in my basement. And I also understand those people.
It's interesting. It's almost everywhere you ask that people are looking for people.
Yeah.
I wonder where everyone is. Is everyone just busy
we
mining
just educated
or
the
selling
wrong
crypto? Or
it was a few weeks ago that LG could not provide the supply, the demands they had, because they just did not have enough technicians to build their batteries. And I don't know, they built half the batteries of the world. And I really am surprised. In 10 years, you say you want everybody to do solar. Who is going to install them? And I don't think it's only my radar. Even the Ministry of Education have mentioned, who is going to do the transition for you, even if you know the solution.
Thanks.
Yeah, and also something I do think what we do need to work on is making sure that people get the reward and recognition if they work on open science or open hardware projects. So you were telling about your nano CET, the microscope. You're very proud of it. You have a patent, and that also sort of helps with this reward or recognition. A lot of people ask for, oh, how many patents do you have? But I do think there's also still a way to go where we recognize that working on open science or open hardware projects is very important and very valuable. And
I agree, and I also disagree with you. On a grand scheme of things, I agree, but I think the emphasis of this recognition reward has become a sort of a go-to excuse a little bit. I understand that the grand scheme of things of, I don't know, 10,000 researchers, universities, and over the course of 10, 20 years, you would like this to have a higher, rank in the visibility. But the day-to-day, I said, we have the money, we are paying you. Dutch salaries are not really small. I could have, hired 5 people like this if I had access to India, and the companies do that. So skills, there is a goal, at least a good motivation, I would say. There is playful, we are having fun. So there are a lot of things exist, and I think the people is the main problem, right? People even have chosen the wrong motivation, or not, a different motivation, let's not call it wrong, or are not trained for this combination of needs. Yeah. I wish we had, I don't know, 5 Santosh and 5 Jerrys, and we could have copied them. Would have been fantastic.
I mean, one of the things we are trying to do is to enable what you're talking about, Sanli, is like, the right motivations and different things. Recently we've had conversations about how if we are supporting events or supporting young people, entrepreneurs, to show them that there are other options available, right? A lot of the time the default is to be within the existing model of doing things. So I think what we want to do is to essentially showcase the possibilities. And I know you're tired of the rewards and recognition part, but at the Tutor for the Open Science program, we are also engendering that to create an option where, well, you're a researcher, you have option of doing 2 different things. One of them might get you patents and it helps you out in one way. Another thing, you really like the project, but if it doesn't, say, for example, move your career forward, it doesn't help to show that you're doing something, I think the rewards recognition really do boost that. So we do have a rewards recognition program on that, I think. But you're right, I think there has to be different things to address different questions at different levels. And yeah, at the Open Hardware, that's what we're trying to do, to attempt at different levels.
Jeroen has a different hand, or is it the same hand, or?
Oh, sorry, I should lower it.
Okay.
that's no problem. And
I can repeat, if you know people who can be interested and perhaps looking for from 1 month to 1 year to 5 years, if you know them, just send them my way. We do have positions.
yeah, we will make sure to also get your contact details in an email afterwards about this event. And yeah, we will make it as easy as possible to get in touch with you. And I think, yeah, in the end, we cannot clone all of the people here in this meeting, but we can, yeah, just keep on organizing cool and interesting stuff. And I think from there on, yeah, slowly people will hopefully get inspired, learn some new things that they find practical, and then, yeah, build and grow this community together. So we just need to keep plowing on, I would say.
Thank you very much.
I think with that, the main part of the event is done. I just want to again thank Sanli very much for giving an excellent presentation. I've been to other talks of Sanli's before, and it's always a pleasure to listen to him talk and always learn something new. So I'm really glad that our 2022 launch was with Sanli. Nicholas, that he mentioned, who worked on the project, is a part of our open hardware community at Delft, and yeah, we also want to foster more people to collaborate. But yeah, ultimately, the human capital is the most important aspect. I think that I can definitely agree with on. I think for the concluding part, Jerry is going to talk about our future events and what we have in store, but also some of the projects that we've worked with within open hardware community for a quick showcase. So yeah, stick around for that. Jerry?
Yeah, thank you. So basically, we are developing this open hardware community, and we are working on maybe our own open hardware projects, but also community projects. And one of our goals is also to for example, show and share this practical knowledge. So over the years, I've gathered some knowledge about printed circuit boards, for example. And next month, we will have a workshop, something which is a bit more, hopefully physical on site, but also it should be able to follow it along online. There will definitely be a live stream, a Zoom event, but basically around making a printed circuit board. So if you have a project with maybe an Arduino and some sensors, and then transforming this from something on a breadboard with a lot of wires poking out to a neatly organized printed circuit board where you can just plug and play modules, or you can solder them directly on it. Hopefully in a later workshop, we will also be able to print a case for such a PCB, and just also some general knowledge and sort of standards used in printed circuit board making, so that it's also easy for other people to understand it, to document it, and to be able to share that. So that is something we will be organizing on the 18th of February. And after this event, we will send out an email with the summary of this event, but also the invite for next event. So with this, you guys are the first one to know about the event, but also the first ones invited. So if you feel like getting a bit more hands-on and learning more about printed circuit board making, then please come and join us. Other than that, if there's also maybe questions about the Delft Open Hardware community itself or projects that we are doing, then please let us know. Santosh, do you have anything else you want to add to that?
I was just going to say, people can join us, Open Hardware community, by meeting up with us on Telegram. I'm just going to add the link to the Telegram channel on the chat. Apart from that, as Jerry mentioned, we have the February 18th event. We're also planning for events going forward. If you have suggestions for an event, or if you have suggestions for speakers as well, please feel free to let us know. We'll definitely consider that as well. Apart from that, anything else, Jerry?
No, I don't think so. Hopefully soon we can meet in person, and we can also invite, for example, Sanli over to the TU Delft. I know he's really looking forward to come and visit us at some point. But I think that's about it for now. Also, Sanli needs to go back to the lab. There's a lot of work to do. So yeah, thanks everybody.
Thank you, everybody.
And hope to see you again next month. And if you still have questions, speak up now or share them somewhere.
Thank you all. See you then next month.
Bye-bye.
Ciao.